All right, well, let's get any questions at all before we get going? Yeah, we got for a few minutes if you want. So it warms up. Like playing. It is chilly today, isn't it? All right. Well, last time we talked about some specific expected values, namely the mean and the variance. So these are more examples of that today. We've also talked about properties and expected value. We'll have a similar property for variance here in a minute. And you can see part E here, I'm going to talk about something specific for variance. And then a couple of other definitions as far as expected values go. You'll notice in the part F of this problem, the next problem in your packet that we have not done yet, there's this idea of coefficient of variation. And then later on, we'll also talk about a way that we can measure skewness, and we'll talk about that when we get to it. Okay. All right. So let's just remind ourselves about different ideas here through the course of this problem. We've got a probability distribution for the value of a share of stock after a year. They tell you the probabilities for 3 of the 4 possibilities. Of course, we can figure out the 4th by doing what? Yeah, 1 minus the sum of the other ones, right? So we can figure out what that value of smiley face is by adding up the other values and then subtracting from 1. Looks like when you add up those other ones, you get what? 0.95? If I added it correctly? Yeah. So this value here should be 0.05. So if we want to figure out what the expected value is, how do we do that again? Yeah, so the definition is the sum over everything in the sample space, right? Oops. Right, element symbol looks goofy. Of x times the probability density function, right? In this case, the x is the random variable that is the stock value. So what values can x take on in this case? Yeah, 0, 50, 100, 200, right? And we'll multiply each of those by the probabilities. Obviously, the first one, I don't really need to do the product since I'm multiplying by 0, but I'll write it down anyway. Then we've got 50 times 0.12, 100 times 0.09, and 200 times 0.05. Okay. 50 times 0.12 is 6. 100 times 0.09 is 9. So we got 15 there. That is what, 10? 19? Or did I say, oh, I'm sorry, not 19, plus another 6. So it's 25? Okay, good. Not too late.
I was expecting it to run a lot longer.
All right, so the expected value of the stock at the end of the year here is then $25. Notice that it's not very likely that you're going to make any money on the stock at all, since you've got 3/4 of the time roughly it's going to fall to 0. By the way, this is obviously a very simple example, a simplistic version, but this is how stocks are priced. We're doing expected values of what the stock's supposed to do in a particular amount of time. That's how they get priced, based on information from the market, previous performance of the stock, and all that good stuff. So these things get priced. Anyway, that's how you would know how much you would want to pay for it, especially other types of, there's a whole bunch of things in finance that you can do. It talks about pricing different options on different things, which I'm not going to go into at all. If you're interested in financial mathematics at all, you get into that stuff. There's a lot of probability that goes into pricing different things. All right. For variance, let's recall again how variance is actually defined, and then our working formula to help us actually evaluate it. So as far as how variance is defined, how do you define what the variance of a random variable is? It's the expected value of what? Good, yeah, it's x minus the mean squared, right? It's that expected value. That's the definition of variance. Again, we call the x minus the mu the deviation from the mean. So this is the deviations. Remember, again, if I eliminate the square and just look at the expectation of the deviations, what do you always get? 0, right? That always turns out to be 0. So that wouldn't tell us much about deviation of anything, right? The expected value is always 0. So we came up with a couple of different possibilities that we might try to get a better measure for how widely spread the data are. We could use absolute value. That would make everything positive, but from a calculus perspective, absolute value is a little bit more troublesome because it's not differentiable everywhere in particular. And there will be times where we'll want to differentiate things. So using squaring instead gets rid of that non-smooth piece with absolute value. Okay. All right, that's the definition, but that's not typically the working formula. What's the working formula that we typically use? Good. Yeah. The expected value of x squared minus the expected value of x squared, right? That's typically our working formula, so let's use this working formula to figure out the variance. In this case, we already have expected value of x in the previous. To get an expected value of x squared, what do you need to do with this summation? Just square the x's, right? So expected value of x squared here will be 50 squared times 0.12, 100 squared times, that actually where it looks like an exponent, times 0.09, plus 200 squared times 0.05. Of course, there'd be a first term there with a 0 squared, but that's still 0, so I didn't bother writing it. That one I don't feel like doing in my head, so if someone wants to help me out with the value, that'd be great. 3,200? So then when we do the variance, we'll do 3,200 minus 25 squared. 25 squared is 625, so what do you get, 3575? Or not 35, 2575? Again, even though our working formula has a subtraction in it, remember this comes from the fact that we're doing the expected value of a square, so this value can never be negative. If you get a negative value out of this, you've done something wrong somewhere along the way. This could never be negative. It can be 0, but again, the only time it can be 0 is if you've got a 1-point distribution, which is also not terribly interesting. Anytime you've got more than one possibility for your random variable, your variance has to be positive and not 0. Is that okay? All right, so then the part C is asking you basically a kind of a concept question. If you expect the value of the stock to be worth $25 at the end of 1 year, and it currently costs $30, should you buy it? No. Because what should you expect to lose? $5, right? All right. If it costs 30 and you expect it to be down on the average to 25, you're going to lose money, so you wouldn't buy it. All right. This one is a little bit, they're telling you a different way to calculate it, but I wouldn't do it this way. I would use your properties of expectation instead, because we've already talked about that. Remember that your expected value of, say you had AX plus BY, so you had two random variables. It doesn't really, let's not do X and Y. Let's just do A, F of X, and F's a bad letter. I think I used U and V before, so I'll just stick with that. If you have expected value of a constant times a function U plus another constant times a function V, how can you rewrite that? Yeah, you can split it up over the sum and pull out the constants, right? Right? And then one last little thing, if I didn't have a function, if this function was a 1, say, and so I just had a constant t there, then we know the expected value of a constant is just that constant, right? So, going back to the problem that we're being asked about, part D, the hint they gave you is unnecessary because we know these properties for expected value. My guess is that, or whatever book I got this out of, they hadn't talked about the properties of expected value yet. I just wanted you to play with the numbers. But in any event, if I want to start with expected value of 10x minus 300, how can we rewrite that? Good. I can break up the expected value over the difference. I can pull the 10 out of the front from the expected value of x. And then expected value of a constant is just the constant, so I don't need an expected value on the end. So I get 10 expected value of x minus 300. You know what expected value of x is. It's 25. We just found it, right? Oops. So you get an expected profit of negative 50 on 10 shares of the stock, which makes sense, right? You lost 5 per share for 10 shares. This one was more of a little bit of an interesting thing for just making sure we remember what the properties of expectation are with regards to constant multiples and sums and differences. Does expected value break up over products? No, not generally. But okay. We can get a similar property for variance. Let's see if we can do that off to the side here. All right, so let's say you wanted the variance of some, and we'll just do it times an x. We'll do the variance of the random variable. So variance of ax, a constant times x, plus another constant. Using, again, our working formula for variance, it's expected value of the variable squared minus the expected value of the variable quantity squared, right? We agree? Okay. So in this case, I'm just treating that ax plus b as a single variable and just plugging it into our formula. And then from here, we're just going to do some algebra. Okay. So inside the first one, we can distribute so you'll get a squared x squared. That should be a 2ab. 2abx plus b squared. Sorry about that. And then in the other one, I will distribute my expected value before I square. So inside the brackets, we'll have A, expected value of x, plus B. So notice you have to do it in the reverse order, right? This one I'm going to square first and then do the expected value. This one we're going to do the expected value first and then square. So that was why I did it in that order. All right. In the first one, how can we break up the expected value here now? Good. Okay. Good. Again, expectation is linear. It breaks up over sums and constants pull out. That's what linear means, right? I can break it up over sums and I can pull out the constants. In the other one, I'm going to square it just like I did in the first one. And then I'm going to also distribute my minus at the same time. So notice that we'll get minus a squared expected value of x, quantity squared, minus 2ab expected value of x minus b squared. Notice that second, when I just squared it in the second case, my expected value of x is playing the role of just the x, right? So it's the exact same distribution. I just take out my x and put in expected value of x instead. Anything go away? If b squareds go away, what else goes away? The 2ab expected value of x, right? Thanks, Alton. Yeah, these go away, right? Those cancel each other out. Those go away as well. Can I factor anything out of the remaining two terms? A squared. And then I'm left with expected value of x squared minus, minus expected value of x quantity squared. What's a better name for this? Variance, yeah. This is a squared variance of x. All right, so here's where we started. Here's where we ended. First, the plus b didn't do anything. Remember, variance is a measure of spread. All your plus b is going to, think about what your plus b does graphically to a function. What does it do? Shifts, right? Depends if it's on the inside or the outside, but it's just a shift, right? Does it actually change the shape of the graph at all? No. So if I add a constant, am I going to change the spread? No. Okay, so it makes sense that the plus b part goes away. Okay. Notice, however, that even if this constant is negative, notice that when you pull it out, it becomes the square. So that's never going to be negative, right? Which also makes sense. Remember what I told you about variance. Can variance ever be negative? No. So if this were a negative, even if I pull it out, it still couldn't be negative because I said that this is the variance of something, right? So I know something's going to happen to that constant. It turns out it's squaring. All right, so let's go back to the problem then. How we have, maybe, here it is, asks you to calculate the variance. We want the variance of 10x minus 300. According to what we just proved, we can rewrite this as what? Good. Yeah, 10 squared times the variance of x. And we just found the variance in the previous step over here. So you get 257,500. Multiplication by 100 is something I can do in my head. That okay? So variance behaves, well, in this case, variance behaves how you would expect it. Variance of a constant is 0, because again, when we do if we just have a constant, there is no spread, right? There is no change. So variance of a constant is 0. When you pull constants out in front, you have to square them. Now, if I actually had two variables here, if I had to say I want to do a variance of x plus y, then there's some other pieces of information that's in there, which we'll talk about when we get to bivariate distributions later. This okay though? That's not too bad. All right, part F is a new term, coefficient of variation. Well, the first, I guess in part B I didn't actually do standard deviation. Standard deviation is just the square root of your variance. That's all it is. So we found the variance before. So for our purposes, the standard deviation will be the square root of 2575, which I don't believe is a perfect square. Should be a little bit bigger than 50. Yeah. Yeah. What is it, Austin?
Be 50.74.
Okay. Yeah. A little bit bigger than 50. Doing the square root of your variance is an attempt to try to undo the squaring we did when we calculated the variance. It's not quite an undoing because, again, when you're doing expected value, you're doing a sum of things that have been squared, and square roots don't break them over sums. But it's a measure of how far data points are from the middle, or not from the middle, from the mean on average. What it's supposed to be giving us. That's standard deviation. Remember, again, we used the little sigma squared to denote variance, so we use a little sigma to denote standard deviation of a distribution. And if you want to specify the distribution, if you've got more than one distribution going along, you'll put a little subscript on there for what the distribution is. In this case, they called the random variable x, so they put a little subscript of x on there, which I didn't bother writing because we've got exactly one distribution problem. Coefficient of variation is another kind of a scaling measure. If I have a standard deviation of 50, that may sound big, may not sound big, depending on what the quantity is you're trying to measure, right? If you've got really, really, really big values, like values that are in the millions, then a standard deviation of 50 is pretty small, right? But if you've got values that are between 0 and 200, like these are, 50 is pretty big, right? So the idea behind this coefficient of variation is trying to scale the standard deviation relative to how big the mean is, okay? So your coefficient of variation is defined as the standard deviation divided by the mean. It's just trying to give you a measure of scale. If you've got really, really big numbers and a small standard deviation, there's not a lot of spread to your data, right? But if you've got a big standard deviation and a smaller numbers, then this is pretty spread out. This is trying to give you a measure. So in this case, you would take your square root of 2575 and divide it by, what was it, 25 was our mean? That's going to be a little bit bigger than 2 in this case. And again, it's a relative measure relative to other distributions. You're basically trying to compare them. So if you've got a coefficient of variation of 2, that would be more widely spread out to something that has a coefficient of variation of 0.5. It's really just a measure of relative spread outness, for lack of a better term. That's all it is. It's, if you're doing data analysis types of things, it's going to be more important then. Right now, we're just giving you a definition and how to compute it. We're not doing much data analysis right this second. Yeah, Kevin? Yes. Yep. Mean and expected value of x are the same thing. Yep. All right. Any questions on that problem at all? Not too bad. All right, so this one, you can tell is a sample actuarial exam problem. Basically, it's just asking you to figure out the mean, figure out the standard deviation, and then calculate the percentages the percentage that's within one standard deviation of the mean. So what that means is, let's say you went through this problem. We haven't done it yet. But let's say you went through this problem. You found out the mean was 55 and the standard deviation was 10. Then you're looking for the percentage of data points that would be between 45 and 55, or 65. Okay, so the mean was 55 and the standard deviation is 10. You go one standard deviation below is 45. One standard deviation above is 65. And you're looking to see what the percentage is between those two values. So in that case, notice I've got discrete data points of 20, 30, 40, 50, 60. If I wanted between 45 and 65, I would just look at the 50 and 60 values. So there's nothing in between those. So you'd say it was 30%, which clearly is not being answered since the answer was given multiple choice. Okay. All right. So again, calculate the mean, calculate the standard deviation. Well, to calculate the mean, I've got to do expected value of x, right? We've got claim size times probability, so we're just going to multiply all the way down. If I can write this correctly. So again, we're just taking each x value that's possible, multiplying it by the probability associated with that x value. And I hear people tapping away. So my squares. Anybody get the first one yet? 55. Hey, I even said 55 a minute ago. So to get our variance after we found expected value, we want to find the expected value of x squared. It's almost exactly the same computation. We're just going to square each of our x values. Did you get expected value of x squared too? 3,500. So then the variance would be that 3,500 minus the 55 squared. $475. Okay. And then so your sigma will be the square root of that. What is that? It's between 21 and 22. 21 point something. Thanks. Yeah, 21 squared is 441, 22 squared is 484. So I knew it was closer to 22 than 21. So a little bit less than 22. So we're looking for, it says within one standard deviation. So we're looking for claims that are between 22 less than that. 22 less than that is about 33, so a little bit bigger than 33. And a little bit less than 77. Well, a little bit bigger than 33 means we start at 40. And a little bit less than 77 means we start at 70, right? Because there's nothing in between. Right? This is discrete data. right? Not continuous data. 40 to 70 here. That's 25, 35, 45%. So it'd be A. Yes. Okay. So again, we want claims between 55 minus 21.79 and 55 plus 21.79. Okay. So 33 and 77, but I can't go to 30, that's too far. So it has to be 40, 50, 60, 70, and then above that's too big. Right? So the possibilities are 40, 50, 60, and 70. Right? And your probabilities then were, don't remember, 0.05 plus 0.2 plus 0.1 plus 0.1. You get 0.45. So that's the 45%. Is that okay? All right. So why would you care about such a thing? Because right now, I know it's a little bit. Why do I give a crap at all? Right? And that's a totally normal reaction. Honestly, right? We're just doing calculations. Well, if you've done anything with statistics at all, one of the things that you use is a normal distribution. Normal distribution, in a normal distribution, 68.24 roughly percent of your data is within one standard deviation of the mean. This has 45% of your data within one standard deviation of the mean. So this is not a normal distribution. It's one of the things that you might be able to tell from that. So that's one of the reasons why we do these different types of calculations, is telling you a little bit of something about the distribution. Okay. It makes more sense when you're doing more data analysis types of things than right now than when you're just learning it. Right now we're just playing with it. Okay? Getting the concepts down. That's why if you were to continue on, this is a whole year-long sequence of courses, not a semester course. Okay? There's a whole mathematical statistics course that comes after this one that tells you more about how you use this stuff. Okay. All right. Any other questions about that one before we're going to do another one? All right. What do we have next? Cool. All right. This is another one of just play around with the different properties. This one's talking about, it gives you an expected value of x is 2. It gives you the expected value of x cubed is 9. And it tells you the expected value of x cubed minus 2 quantity cubed is 0. And then asks for the variance. Before we do this problem, let me give you a couple of other definitions that we haven't mentioned yet. Okay. When we have the expected value of x to an integer power, typically the textbooks use r, and I don't know why they use r, but the r is a positive integer power. This is called the rth moment of x. So your expected value is your mean is expected value of x, right? X to the first power. So this is your first moment. Expected value of x squared is the second moment. And so on down the line. So what they've given you here, they've given you the first moment. Oops. Oops. And they've given you the third moment. Okay. To calculate the variance, we're also going to need to find the second moment, right? Because when we do the variance, we do expected value of x squared minus expected value of x quantity squared. So your variance is second moment minus square of the first moment. Talking about in terms of moments. Notice this other one is also a moment, if you will, because I'm doing expected value of x cubed again, but I'm subtracting a number. If you do expected value of x minus some constant to a power, then that's the still called the rth moment of x, but it's about a constant, about b. Yes. That would just be about negative b then. It would be minus a minus b. It's whatever the number is there, it's x minus whatever the number is. So if it's a plus b, it would be the moment about the opposite of b. If you write it as minus a minus. We've talked about, one of the things we've talked about is a moment about a number. The variance is the second moment of x about its mean. Because remember, it's expected value of x minus mu quantity squared, right? There's another value that comes out of moments, and that's the idea of skewness. When we do skewness of a distribution, by definition, it's the expected value of x minus mu cubed, and then divided by the standard deviation cubed. We'll do a calculation. Well, notice in this case, your expected value, in this particular problem, your expected value of x minus the mean, because they tell you the mean is 2 here. The expected value of x minus the mean cubed is 0. So it has its skewness is 0. What that means for a distribution is that it's symmetric about its mean. There's as many data points below the mean as there are above. Nice and symmetric about it. So the skewness is a matter of what is going on with the distribution as far as the shape of it, if you will. And we've talked a little bit about shape through histograms and bar graphs, right? And we'll come back to that when we do continuous distributions as well. We'll do a calculation of this in a minute with a problem later on in the packet. But let's go back and just answer the question they've asked. Okay. All right. So we have the first moment and we have the third moment. And we have the third moment about 2. So we should be able to use that information to figure out the second moment. Okay. So let's look at expected value of x minus 2 cubed equals 0 and see what substitutions we can, or what algebraic simplifications we can do and what substitutions we can make. What do you get when you multiply that out on the inside?
X cubed minus 6x squared plus 4x minus 8.
Good. We multiply all that out, you get that. And now again, we know that our expectation is linear. So how can we rewrite the left-hand side?
X cubed minus 6 x squared plus 12x minus 8.
Good. That's just breaking up our expected value over the sums and differences there and pulling out the constants. And we have values for these things, don't we?
Expected value of x cubed is 9. I don't know expected value of x squared. Expected value of x is 2. Uh, 9 plus 24 is 33 minus 8 is 25. Did I do my arithmetic right? Okay. So I'll subtract the 25 over to the other side. We get our expected value of x squared is 25 over 6. I was expecting it to come out an integer rather than a fraction, so why I paused a second ago. All right, so do we have enough information now to figure out the variance? Yeah, we just need to take that 25/6 and do what? Good. And they tell you that e of x is 2. So 4 is the same thing as 24 over 6, so I get a 6th when I'm done. That one okay? Again, not a terribly interesting problem in and of itself. It's more along the lines of just playing with the properties again, making sure you understand how expectation works with regards to sums, differences, and exponents, right? Because I know I can't pull the exponents out, right? So more about playing with those different things. Plus, it gave me a chance to define some terms that we hadn't defined yet. Questions on that one? Bless you. All right. Well, here's one where it asks to calculate the skewness. Look at that. All right. So, in order to be able to calculate the skewness, remember again, that's the expected value of x minus the mean cubed over the standard deviation cubed, or the variance to the 3/2 power, whichever way you want to look at it. If you have done Calc 3 and did curvature, I believe there's a 3/2 power in curvature formula, isn't there? It's a magnitude of the derivative of the position, the second derivative of the position function cubed, if I remember correctly, in Calc 3. You do a magnitude of a cross product and then divide by the magnitude of a derivative cubed. So there's a 3/2 power that's in there. It's been a while since I've taught Calc 3. I don't remember it. I don't do it off the top of my head all the time. Okay. I think it's if I remember correctly, it's the magnitude of the position cross its derivative over the magnitude of the derivative cubed. I remember right. In any event, magnitude has a square root in it, and you do the third power. That's a 3/2 power, right? That's a 3/2 power as well. That's 3/2 of your variance. I'm just trying to point out there's some similarities with curvature. If you've had differential equations, what we're going to do here in a minute or two has some similarities to Laplace transforms. So if you've done differential equations, you've seen Laplace transforms. If you're taking differential equations, you will see Laplace transforms. In any event, that's what we have to calculate for skewness. Sorry. Just wanted to just try to relate things to other classes because everything is connected. Students love to compartmentalize things. I'm done with this. I don't ever need to think about it again. That's not typically how math works. All right. In any event, in order to be able to do this, you can either do what we did before and multiply out something that looks like this, right? But in this case, I think it's just as easy, especially since we have a small, relatively small distribution, to actually calculate your mean and then just do your expected value using the cubed formula there, rather than trying to multiply it all out. Because if I multiply it all out, I've got to find expected value of x, expected value of x squared, and expected value of x cubed. I've got to do 3 things, right? Because notice when you multiply it out, if I scroll back up again, right? Because you'll have an x cubed, an x squared, and an x in there. Just messy. So either way, doesn't matter which way I do it, I have to figure out expected value of x, right? The reason why I have to figure out expected value of x is because that has to go right here. I need to know what that mu is. Okay. So I take 100 times 0.05, 200 times 0.2, 300 times 0.5, 400 times 0.2, 500 times 0.05. Did anybody do that already? Thank you. Saves me brain power from doing it in my head. Okay. Actually, I guess technically I do have to do expected value of x squared anyway because I need to do my sigma. Yeah.
So if it's symmetric like that, could we have just known it's 300?
It's not quite symmetric. Oh, this one is 300. It's symmetric. Yes. Then there's actually no point in doing the rest of the problem. Actually, now that you say that. Okay, good. That's actually a good thing. I was actually going to go do the actual problem, but you're exactly right. This is symmetric, right? About the mean, we've got an equal probability at an equal distance, and an equal probability about an equal distance. So you're exactly right. I would know it was 300. Well, if it's this, and if it's symmetric, then I know the skewness is 0. Okay. So I can actually quit there. Okay. I'm not going to quit right this second because I just want to illustrate what you have to do if it's not symmetric. I need to calculate that, right? I need to do x minus 300 quantity cubed. And then I would also need to do the standard deviation, but I'm just going to do this part. So in this case, you would have 100 minus 300 cubed times 0.05. I didn't even notice it was symmetric when I started. I would just do it this way rather than multiplying all out your whole cube formula. And you should get 0 when you're done with all of this. But as Austin already noticed, this is negative 200 cubed. That's positive 200 cubed. So those are opposites of each other, and you're multiplying by the exact same probability. Same thing happens with these two terms. So those will cancel, and that is 0. So you'll get 0 when you're done. So the skewness is 0. All right. To illustrate that and then talk about what the skewness measures, in this case, if you were to do, let's say, a histogram, you'd have something that looked like this for 100, and then that for 200, and then that for 500, 200, 100. And that's symmetric right about the mean, right? So that would be what our skewness is 0 here. Okay. But what would happen if you would have had maybe something that looks like this? For a distribution. Where it's not symmetric. Where is your probability more loaded? At the low end or at the high end? At the low end, right? Because notice here at the right, it drops off very, very steeply, correct? So your probability is more loaded to the left than it is to the right. So if I do that x minus mu and cube it, these are going to get weighted more than those. So your skewness here will be negative. If I could spell the word skewness, that would be helpful. So we say that's skewed left in that case. Notice if I look at where this would peak out here, my mean gets pulled to the left. That's what's getting skewed, is the mean's getting pulled down from the high point. The reverse image would be positive skewness and skewed right. We'll come back to those pictures later on when we do a continuous distributions, where we can see the picture a little bit better than me trying to draw a bunch of rectangles like that. Okay. Questions on that at all? All very happy with all of it? All right. Here we go. Told you we're going to come to another idea that looked like Laplace transforms, and that's the idea of what we refer to as a moment-generating function. So we did the definition of moment a little bit ago, what we mean by the moments. So the moment-generating function must be something that generates the moments of the distribution of the probability density, or the probability mass function, the random variable. All right, so how do we define the moment-generating function? Oops. And again, if you've seen differential equations, this part should look familiar. The moment-generating function of a random variable x, this is going to be a discrete random variable, but it works also for continuous random variables, is we typically use the capital letter M to denote moment-generating function. If we have more than one random variable floating around, we'll put a subscript of x there. This is going to be the expected value of e to the tx. Or if I write it as a summation notation, it looks like that. If you've taken differential equations and you replace that summation with an integral sign, that is the Laplace transform. Okay? If you've seen differential equations, that's exactly how the Laplace transform is defined. Why do we care? It's a good question. Why do we care? Right? So it's supposed to generate moments. Remember, your first moment is expected value of x, right? All right. Well, given the way that this is defined, notice that the reason why my input here is a t is because when you do this summation, you're plugging in values for x, right? And then that's the t that we have left over. Okay? As long as this summation converges for some positive values of t, some values in an interval containing t, not just at 0. As long as this converges, I can do derivatives. Remember doing power series stuff? As long as you had convergence around some little interval, you can do derivatives. All right? So let's do the derivative here of the first derivative of your moment generating function. Well, man, this thing is just making my handwriting look terrible for some reason. I'm going to do the derivative with respect to t of that sum, but even if it's an infinite sum, I can still pull the derivative on the inside, provided it converges, right? If I pull this on the inside, again, we're differentiating here with respect to t, right? Not x, but with respect to t. If I'm differentiating with respect to t, we treat x as a constant, correct? What is the derivative going to be?
e to the tx.
And then f of x, right? We agree with that? Notice what's popped out in front here. Got an x when I took the derivative, right? I have an extra e to the tx in there, but I have an x that's there. How can I make this, what can I plug in for t? Because remember, this is a function of t. What can I plug in for t to make this disappear? 0, right? Because if I make it a 1, and if I make it this disappear and make it a 1, what is that? What do you recognize that as? Expected value of x, right? Which is the first moment, correct? So if I do m prime of 0, I get the first moment. Right? What if I decide to differentiate again? If I differentiate again, what's going to go right here? X squared, right? So if I take the second derivative and plug in 0, I'll get the second moment. And in general, if I take the rth derivative and plug in 0, I get the rth moment. That's why we call it a moment generating function. You have the function with respect to t, as long as your series, or later on, we'll do integrals when we do continuous distributions, as long as it converges for some values other than at 0, I can take derivatives and I can generate moments in this fashion. Okay? All right, so going back up to the problem, they give you the moment generating function, and it asks you to find the mean and the variance, and then recover the probability of mass function. Ooh, that's interesting. That's fun. Okay. That's one of the more interesting things about moment generating functions as well, is that if you know the moment generating function, you know the distribution. You can tell what the distribution is based on its moment generating function. Okay. And we'll talk about how to do that here in just a second. But let's do the mean and the variance. I need first moment for mean. I need second moment for variance, right? So first thing I want to do is I'm going to differentiate my moment generating function, get my first two derivatives. What is the first derivative?
2/5 e to the t.
Okay.
2/5 e to the 2t.
Good.
And 6/5 e to the 3t.
Good. And let's go ahead and do the second derivative while we're at it.
E to the t. 4/5 e to the 2t. 18/5 e to the 3t.
We okay with derivatives? I hope. Hope you're okay with derivatives and integrals, because we're going to do those later too. All right. Expected value of x using the moment generating function is plug in 0 for t. Well, e to the 0 is 1, right? So for expected value of x, we get 2/5 plus 2/5 plus 6/5, which gives us 2. And expected value of x squared is the second derivative evaluated at 0. We get 2/5 plus 4/5 plus 18/5, 22, 24/5. Is that second piece your variance? No. This is your mean. Your mean is 2, right? Expected value of x is the mean. That's 2. But our variance is going to be 24/5 minus 2 squared. That's 20/5, so you get 4/5. Right? We're doing expected value of x squared minus expected value of x quantity squared. Right? Any questions about mean and variance in this fact? We're going to do more examples, but any questions about mean and variance based on this? No. Okay. All right. So let's talk about how we recover the PMF. That seems hard, isn't it? Okay. Seems hard, right? Sounds hard. Okay. All right. Let's go back up here to how we defined the actual moment generating function, right? We do expected value of e to the tx times f of x. Right? Now, especially if I have a finite sum, this is pretty easy to recognize. Because again, if I'm going to do this sum, pardon me, if I'm going to do this sum, things have been plugged in for x, right? If I'm looking at this moment generating function, how many terms are in the sum? 3. So how many different x values do you think we have? 3, right? Looking at the form, especially on my e's, what's been plugged in for x in each of these terms? That one has an x value of, that one has an x value of, and that one has an x value of 3. So can you identify the support? Yeah, x equals 1, 2, or 3. All right? Now, it says recover the PMF, all right? Notice what's on the coefficients here. I have e to the tx times f of x, all right? So what do you think the coefficients for each of your e to the whatever powers, e to whatever powers are? What do you think those are? I've got e to a power times something. What do you think those somethings are? Yeah, the 2/5, those are probabilities associated with those x values, right? It has to be, f of 1 has to be 2/5, f of 2 has to be 1/5, f of 3 has to be 2/5. There's your PMF, right? So your PMF here, I guess I'll write it off to the side because I've wasted all that page. Your PMF will be 2/5 if x is equal to 1, 1/5 if x is equal to 2, maybe, and 2/5 if x is equal to 3. So if you've got a finite sum, it's pretty easy, relatively speaking, to identify your support and what the probabilities have to be. Your support comes out of the coefficients on the t in your exponent, right? We saw e to the t, e to the 2t, e to the 3t. So that's 1 times t, 2 times t, 3 times t. So the support was 1, 2, 3. And then the associated probabilities with those pieces in your support are the coefficients on those terms. The 2/5 was the coefficient on the e to the t, so that's the probability of x as being 1. 1/5 is the probability for x being 2. 2/5 is the probability for x being 3. Just pull them right off. That okay? All right. This one's a little bit different. This one also looks hard, but it's not too bad. They tell you that you've got a random sample from a discrete distribution. All random sample means is that each of your observations are independent of each other. We've done independence, right? So in this particular instance, x1 can have a value of 0 or 1, x2 can have a value of 0 or 1, and x3 can have a value of 0 and 1, and whatever one value is has absolutely no bearing on the next one. So for example, maybe you associate 0 being, not with those probabilities, but maybe 0 is associated with flipping heads, 1's associated with flipping tails. Okay, so then you're just looking at consecutive flips. Okay. All right. Now in this case, what are you doing with the results that you get? You're taking the value you get for x1, the value you get for x2, the value you get for x3, and you're multiplying. What are your possibilities then for the values for y? If your values for x1, x2, and x3 have to be either 0 or 1, and you multiply them all together, what are your possibilities for the values for y? 0 or 1, right? So your possible values for y let's ask the easier question. How is y equal to 1? What has to happen to get y equal to 1? All three have to be 1, right? So what is the probability that y equals 1? Yeah, 2/3 cubed. Fantastic. Exactly right. There. Remember again, I told you it was random sample. Random sample is just a fancy way to say independent for us right now. x1, x2, x3 are independent. So in order to get y being 1, x1 has to be 1, x2 has to be 1, and x3 has to be 1. So we multiply the probabilities together. And so that gives you 8/27. So what's the probability that y is equal to 0? Oh, that's the hard way to do it. It's just gonna be 1. It's the rest of the cases, right? You just told me it has to be 0 or 1, right? So I can just do the complement. So you get 19/27. Oops. The reason why I said it was the hard way to do it is because you have to do all zeros, or exactly one of them is 0, or exactly two of them are 0. Try that again. All are 0. 2 of them are 0. 1 is 0. You can get there that way. It's just harder. It's easier to do the complement. All right. So now we have the probability that y is equal to 0 and the probability that y is equal to 1. So we should be able to get the moment generating function. How many values of y are in your support? How many distinct values of y can we have that have non-zero probability? 2. So how many terms are going to be in your sum? 2, right? For your moment generating functions, an expected value, right? To do expected value, you sum up over the entire support. How many elements are in the support? 2. So how many terms are going to be in your sum? 2. Yeah. So we're going to have two sums. We're going to have 2 terms in the sum. It's expected value of e to the t, in this case y, times the probability, right? The probability for 0 is 19/27. And then it would be e to the 0t. But e to the 0t is just what? 1. And then you'd have 8/27 times e to the t. So again, if I want to write it down, you would do e to the 0t times f of 0 and e to the 1 times t times f of 1 is how we're doing that. Is that okay? We're just doing an expected value again. Let's see. I'm going to skip that one for the time being because I don't want to deal with it.